Imagine a world where everything you thought you knew about symmetry was wrong, where the patterns in nature were not just beautiful, but the very backbone of the universe itself. What if I told you that one brilliant mind uncovered the true power of symmetry, unlocking the laws of physics and changing everything? Throughout history, symmetry has been admired for its beauty, from art to nature. But what if it's more than just a visual concept? What if symmetry is a fundamental force shaping the universe? Emmy Noether, a brilliant mathematician, uncovered this hidden truth, revolutionizing physics and revealing that symmetry governs the laws of reality. This is the untold story of how symmetry became the backbone of modern physics. What is symmetry? Symmetry is all around us, in the wings of a butterfly, the spin of a top, and even in the designs of buildings. While we often see it as a visual or aesthetic principle, in science, symmetry is much more than that. It's a fundamental force shaping the universe. At its core, symmetry means that certain properties of a system stay the same even after transformations, like rotating or flipping. This idea is key to understanding everything from tiny particles to vast galaxies. But it wasn't until Emmy Noether, a brilliant mathematician, that we truly unlocked the power of symmetry in the laws of physics. Emmy Noether and Einstein. Imagine being a brilliant mind in an era when your gender could determine your success or failure. Emmy Noether, born in 1882 in Germany, faced that very reality. In a time when academic fields were dominated by men and women were often kept at the margins, Noether stood out as a beacon of intellectual brilliance. But even though she was highly respected by her peers, her path was far from easy. Noether's journey into mathematics was a battle. Early on, she was forced to work under the shadow of male professors who didn't always recognize her talents. But Emmy persevered, gaining recognition through her radical new ideas in abstract algebra, a field that would later become crucial for the development of modern physics. Her most significant breakthrough came in the world of theoretical physics, when she began collaborating with one of the greatest minds of the time, Albert Einstein. By the time Einstein was grappling with his theory of general relativity, he was deeply entrenched in the complicated mathematics that underpinned his ideas. But despite his genius, Einstein was struggling to fully grasp the mathematical structure of his own theories. In 1915, as Einstein worked tirelessly to complete his theory of gravity, he sought the help of Emmy Noether. Their partnership was a match made in intellectual heaven. Noether's clarity of thought and deep understanding of mathematical structures allowed her to refine and solidify many of the core concepts within Einstein's theories. But more than that, she showed Einstein the deep connection between symmetry and the laws of physics. General covariance. One of the key insights that emerged from Noether's work, and one that would forever change physics, was her understanding of general covariance. General covariance is a fundamental idea within Einstein's theory of general relativity, and it states that the laws of physics should take the same form no matter where you are in the universe or how you choose to look at them. This means that the physical laws aren't dependent on the specific coordinates you use to measure them. Instead, they apply universally. To the untrained eye, this may seem like a rather abstract idea, but Noether's work illuminated the true power of this principle. In essence, general covariance suggests that the universe is built on symmetries, symmetries that remain constant no matter where you are or how you measure things. It's a principle that speaks to the deep, unchanging nature of the laws that govern our reality. In simple terms, if you can find a system that obeys the principle of general covariance, you found something that is consistent across time and space. Noether's work showed that symmetry wasn't just a mathematical convenience, it was the key to understanding the deepest truths about the universe. The principle of least action. As we dig deeper into the world of physics, another key concept that emerges is the principle of least action. This principle states that, in any given situation, a system will take the path that minimizes the action, a quantity that depends on energy and time. It's as if nature is programmed to take the most efficient route, doing as little work as possible. Now, this principle may sound abstract, but it's actually a foundational idea in many branches of physics, from classical mechanics to modern quantum theory. The beauty of the principle of least action is that it can be applied to a vast range of physical phenomena. Whether it's the motion of a planet, the behavior of a subatomic particle, or the path of light, this principle helps explain how and why things move the way they do. And here's where Noether's theorem comes in. Noether's first theorem, published in 1918, demonstrated a deep relationship between symmetry and the principle of least action. In fact, Noether showed that every symmetry in nature corresponds to a conserved quantity, something that doesn't change over time. For example, the symmetry of time leads to the conservation of energy, while the symmetry of space leads to the conservation of momentum. Noether's insight was groundbreaking. She showed that for every symmetry, there's a corresponding conservation law. This revelation would shape the understanding of physics for generations to come. Noether's first theorem. Noether's first theorem is often considered one of the most profound contributions to physics. It states that for every continuous symmetry in nature, there is a corresponding conserved quantity. In other words, symmetry is not just a nice-to-have. It's a central feature of the universe that governs the behavior of physical systems. Take, for example, the conservation of momentum. This principle tells us that if no external forces are acting on a system, its momentum will remain constant. This law can be derived from the symmetry of space. No matter where you are in space, the laws of physics should apply in the same way. Similarly, the conservation of energy can be traced back to the symmetry of time. The laws of physics don't change as time progresses. Noether's first theorem gave physicists a profound new tool for understanding the universe. By studying symmetries, they could predict and explain conservation laws, which in turn helped them understand everything from the behavior of atoms to the motion of galaxies. The continuity equation. One of the many applications of Noether's work is found in the continuity equation, a mathematical expression that describes how certain quantities, such as mass, energy, or charge, are conserved within a system. The continuity equation is a fundamental tool in many areas of physics, from electromagnetism to quantum mechanics. The equation expresses the idea that, in a closed system, the total amount of a conserved quantity must remain constant. If mass or energy is being lost or gained from the system, this must be accounted for. The continuity equation shows how the conservation of mass, energy, or charge can be linked to the symmetries of a system. Noether's work gave physicists a framework for understanding these processes, showing how symmetries underlie many of the conservation laws we take for granted. It's a direct result of her theorem and has led to numerous discoveries in fields as diverse as fluid dynamics, quantum field theory, and cosmology. Escape from Germany. Despite her monumental contributions to science, Noether's life was not without hardship. In 1933, when the Nazi regime came to power in Germany, Noether, who was of Jewish descent, found herself the target of increasing persecution. She was dismissed from her academic position at the University of Göttingen, despite her vital role in the intellectual community. In the face of growing danger, Noether was forced to flee Germany. She was invited to continue her work in the United States, where she joined the faculty at Bryn Mawr College in Pennsylvania. Though her time in America was short, her contributions to physics continued to influence future generations of scientists. Sadly, Noether's life was cut short when she passed away in 1935, just a few years after escaping Germany. Her death left a profound void in the world of mathematics and physics, but her ideas lived on. Emmy Noether's legacy is a testament to the power of intellectual curiosity and the relentless pursuit of knowledge. Her work on symmetry transformed our understanding of the universe and paved the way for some of the most groundbreaking discoveries in modern physics. If you like this video, don't forget to like and subscribe to our channel for more amazing content like this. See you in the next video.